All right, welcome back. Now we're dealing with Module 5, which is the chemical contaminants rules. And what we'll see, like with the lead and copper, you'll see the lead and copper again in the chemical contaminants rule. We'll look at the inorganics, volatiles, and synthetic organics. So like all the modules will be set up the same way. We'll do the regulatory overview. We'll look at the monitoring requirements for whatever we're talking about at the time, and this time it's going to be chemical contaminants. And then we'll talk about the maximum contaminant level goals as well as the maximum contaminant levels. We'll identify some contaminants of concern. In other words, we'll extrapolate these out of the rules, and we'll discuss the various chemical and contaminant treatment options that may be available. Again, EPA by congressional mandate in 1987 looked at 65 contaminants to review for adverse health effects. Now, prior to 1987, there were not as many that were on the list. And so more and more being added. There are even unregulated chemicals now that they're looking at, reviewing, gathering information. From this 65 contaminants, they established the maximum contaminant level for each chemical. Maximum contaminant level is simply that legal threshold limit on the amount of the substance that is allowed in public water systems. Remember, public, not private. Private systems are not regulated, and that is under the Safe Drinking Water Act. The limit is usually expressed as a concentration in milligrams per liter or micrograms per liter. And again, this limit is set close to the health goal as possible. The health goal is that level which there are no health risks, no known health risks associated with that particular contaminant. The limit is where there is a known health risk, and it's set real close to the goal as possible. So EPA established the following for removal of the 65 chemical contaminants: MCL, that's the maximum contaminant levels, and MCLGs, which is the maximum contaminant level goal. Now, there's no adverse health effect at this level, and these are non-enforceable health goals. So the goals are just that, the ideal, but these are non-enforceable. They also establish what monitoring requirements will be and the best available technology for removal. There were 3 contaminant groups, so like the lead and copper with the 3 tiers, here we have 3 contaminant groups: inorganic chemicals, synthetic organic chemicals, and your volatile organic chemicals. So these were the 3: inorganic chemicals, synthetic organic chemicals, and your volatile. The hexavalent organic chemicals was not one of the group. So you got that one right earlier, Stephen. We do have the regulated chemical contaminants on table 5.1, page 5-4. And on that, you see a whole lot of them listed there. Now, what's ironic is bottled water, which so many people pay so much for, is not as highly regulated as our drinking water source, potable drinking water source.
We just had an incident a couple of years ago, locally, with the bottled water company.
Really? Yeah, possible to find chemical contaminants there depending on what process they're using.
Straight on tap water, he's filling it up right out of the bedroom.
You know, one of the shows did an expo on that, and I think it was Pepsi with the Aquafina.
Yes.
Yes. Tap water we're paying twice for.
Yep.
Heck of marketing. Now, some of the health concerns from these contaminants: cancer, organ damage, circulatory issue, nervous problems, reproductive disorders, as well as the blue baby syndrome. All public water systems must monitor the nitrites and nitrates. Your community water system, non-transient, non-community water system must monitor the IOCs, the SOCs, and the VOCs. Now, because community and non-transient falls up under the public water system, that means that they are monitoring the nitrites and nitrates too. All right, this is not in your book, but we found this to be very, very useful, and that's the standardized monitoring framework. I'll tell you what website to go to. This is an EPA quick guide as to what you should be monitoring and the frequency. All right, and it's called the Standardized Monitoring Frequency, a quick reference guide. And this was promulgated in the Phase 2 rule on January 30, 1991. The purpose was to standardize, simplify, consolidate the monitoring requirements where you see all the contaminants at once and the frequency for each of those. And so this is very, very useful here. Here we see the regulated contaminants. Remember, there were 3 groups: inorganic, synthetic, and volatiles, and the radionuclides, which there are 4 there. For all public water systems, they're doing nitrate and nitrite, as we just said. Communities are also doing the inorganic, the synthetic, and volatile organics, and radionuclides. Your non-transient, non-community system must do the nitrate, nitrite, plus the IOCs, SOCs, and VOCs. But notice, not the radionuclides. So that was one of the things too that was on that exam. They are exempt from the radionuclides. All right, when you see 1 asterisk on this next chart, that means you're going to do 1 sample at the entry point to the distribution system. If you see 2, there are 2 quarterly samples at each, again, entry point. This will be for quarterly. Again, it's not in your book, but I'll give you the website where you can go and get this quick reference guide. And then X, no sampling is required unless your primary agency tells you you have to do it. So, here we have the inorganics. Is that kind of blurry or is that just me? It's a little blurry. Is that a little bit? Okay, that's a little better. Hey, y'all let me know. Y'all are sitting out there. I'm just looking like, wait, I'm right up here and can't read that. All right, for the inorganics, if we have a groundwater system below the trigger level with waiver, let's do the one with the waiver first. How do we get a waiver? First of all, you're going to have to request one. And then second of all, you're going to have to demonstrate that you don't have an issue with that particular contaminant for a certain period of time. So with groundwater systems with a waiver, you're looking at doing the inorganic contaminants once every 9 years. And this is the second cycle, which means that first cycle was your time, to prove, which was once every 3 years, that you didn't have a problem. So after that initial monitoring, and the usual monitoring for groundwater system is once every 3 years. Not a problem, you request a waiver, now you're on the reduced monitoring for once every 9 years. Pretty doggone good. Let's say if you didn't have a waiver, you're still on the same game plan once every 3 years to monitor the inorganics. Okay? Now, if you were above the trigger level, action level, maximum contaminant level, look at the frequency. With groundwater system reliable and consistently less than the maximum control level but above the trigger level, you're still doing the once every 3 years. If you were above the maximum contaminant level, look at that, you're going to once a quarter. Once a quarter. For your synthetic, we see the same scenario almost. Population, that's okay, population above 3,300, but below the trigger level with a waiver, no monitoring whatsoever. Less than the detect with no waiver, again, you're looking at 2 once every 3 years. If you're above the trigger level, you're looking at once a quarter. And likewise with the volatiles. So very quick reference. This takes you out all the way to 2019. I'll give you the website where you can go to. Same with nitrates. If you're greater than 1/2 the maximum contaminant level, you're going to a quarterly basis for your community and non-transient community system, pulling in quarterly. Groundwater, reliably and consistently less than the maximum contaminant level on an annual basis. Standard monitoring is annually. So this is an excellent guide for you that you can look at a glance and be able to determine what exactly you need to be doing. This is the website that you can download this, print it. And that way you'll never have a doubt what's the requirement for your chemical contaminants. As read along, and I think this is an underscore here also. All right. So, again, with the waivers there, monitoring waivers, reduce sampling frequency to once every 3, 6, or 9 years if you've been granted a waiver. For specified contaminants based on vulnerability assessments to show, you need to make sure that you're able to tell them contaminant has not been used in the area, nor does the system or is the system susceptible to that particular contamination in order to request that waiver. And you got to make sure you have the analytical results of the previous sample, which shows that's not an issue. So it makes sense. So you want to make sure when you can get a waiver, talk to your state agency in order to be granted that waiver. But you have to make the request, or you'll be on that continuous cycle with your groundwater system once every 3 years. Maximum contaminant levels are legally enforceable standards. The goals are not. The levels are legally enforceable. The levels, maximum MCLs, are put in place to protect the public health by limiting that particular contaminant that's in your drinking water. Again, I told you you can look at figure 5.1 for the list of contaminants that are there, all the IOCs, VOCs, and SOCs. Also on that chart you have the potential health effect from long-term exposure, the source of contamination, as well as the public health goal. A lot of information there. Now, drinking water may be reasonably to be expected to contain at least small amounts of contaminants. So we expect for there to be some contamination in our drinking water. But again, the goal is to have whatever the maximum goal is. Of course, the level is, maximum MCL is not to exceed that. There are some that we are more concerned with that may fall under the inorganic: arsenic, fluoride, nitrate, radium, and uranium. These are ones that special attention has been given to in this book as contaminants of concern. Arsenic is a semi-metal element. It's odorless, tasteless. It enters the drinking water supplies from natural deposit in the earth from agricultural or industrial practices. What do we use arsenic for? Now, it's true that our body does require very small amounts of it. We also find it in wood, preservatives, paint, dyes, metals, drugs, semiconductors. There is some agricultural application for arsenic that's out there, mining and smelting. But the problem is when you start to exceed the maximum contaminant level, now it becomes an issue. Some of the health effects would be skin defect or damage, circulatory problems, and increased risk of cancer. And the truth of the matter is quite a lot of them will see the increased cancer risk component there. Now the goal, 0. The maximum contaminant level, 0.01 milligrams per liter. Now this is new because it used to be 0.05. So what does that tell you when they drop the limit like that?
Yeah. I mean, I thought it was pretty serious.
Yeah. The lower that limit, yeah, the more dangerous that chemical is. Okay. And that was effective in 2002 with that new 0.01, so that hadn't been that long ago there. Right, we said it enters the water, our drinking water through erosion or natural deposits, runoff from the arcades, runoff from glass and electronic. How many of you all noticed, and I think this was Dr. Oz show, and I'm not promoting his show, where they were talking about the arsenic level in the apple juice? Where was it coming from?
It's coming from pesticides.
Okay, pesticides and all of that, and concentrated in the seeds. So don't let your children eat those seeds or anything like that, because it's a highly concentrated amount of arsenic in those seeds. And so if you're juicing and things like that, make sure you always core the seeds out, because you have elevated levels there. So you're going to, that's how it enters the drinking water, and under the Emergency Planning Committee and Right to Know Act, if you have facilities that are underground and they have the possibility of leaching this out, you have to report annually on the release of these chemicals. Another contaminant that we are concerned about is fluoride. Depending on which side of the fence you're on. And what do I mean by that? That some believe that fluoride is the best thing for tooth, protection. And then there are the others that believe, man, it causes autism and everything else. Yeah, there have been some scary things that it's been tied back to.
Big time.
Yeah, big time.
1938, 1939 is prime time.
Really, what happened in 38 and 39? Educate me on that.
The Russians and Germans used chemical compounds for mind control agents. What it was doing was taking the passive, taking the aggression out of people, making them passive. And slowing down there.
So fluoride,
Fluoride.
that's interesting.
In large dosage.
Right.
Not over a period of extended exposure.
So it'll take you from aggressive to very passive.
Hence the theory of being sheep.
Okay, that's interesting there.
That required it after 1992.
Yeah, for the most part, that is something that, again, a lot of communities and even state, because I'm told that Delaware State said mandated it, that you fluoridate your waters. They have that option to do that. The use is promotion of dental health. Again, it prevents tooth decay in very small, minute amounts. Health effect, though, when you start having large amounts, you're going to start seeing bone fractures or the pitting of the tooth enamel. Initially, it starts out as mottling, which is the staining of the teeth, and then you actually start seeing the pits that are there. Now, this is one that is regulated both as a primary as well as a secondary standard. Now, what's the difference between primary and secondary standards? Primary standards are those with MCLs that are enforceable. Secondary standards are those aesthetic things that we would like to see in our water. There is no health effect attached to it. But I want my water crystal clear and not orange red. Okay? That is an aesthetic deal. So, your primary standard MCL goal, as well as the limit for fluoride, is 4 milligrams per liter. That's when we start seeing the ill health effects of fluoride, when it's above 4. As a secondary standard, it's at 2 milligrams per liter. It's lower. Why? Because when it starts to get up over 2, that's when I start seeing the mottling and the pitting of the teeth. Okay? Fluoride is easily dissolved into groundwater as it moves through the gaps and port spaces between the rock. In other words, the fluoride is your naturally occurring mineral that's in your soil. Water is a universal solvent, so as it flows through the soil level, it picks up whatever impurities that's there, whatever mineral that's there, whatever metal that's there. So it can be naturally occurring, and it's also discharged from fertilizer or aluminum factories. In some cases, it ends up in our drinking water because we put it there. And the reason we're putting it there is to promote good dental health. Okay. So again, as long as it's between the 0.7, 1 milligram per liter, not exceeding 2, we should be good to go with fluoride. Another contaminant of concern is nitrate. Now, who remember why we are concerned with nitrate and nitrites in our water? Blue baby syndrome, very good. Usage for fertilizer. You have lots of crop areas around in Delaware. Okay, and the runoff from that can end up in our drinking water source or shallow wells. It's elevated nitrates. Regulation for the goal, it's 10, as well as the maximum contaminant level, 10 milligrams per liter. Gets into our water source from runoff from the fertilizer use, sorry about that. Leakage from septic tanks. How many septic tanks do you all still operate? Or private people operate? You know, I have quite a few of them still. Because some of the homes are very, very spread out here. I've noticed that outside of the immediate city area. Sewage or erosion of natural deposit there. Another contaminant of concern is the radium. Radionuclides are atoms with unstable nucleus, which to become more stable emits energy in the form of rays or high-speed particles, and that can disrupt the DNA function. There are 3 major types of ionizing radiation: alpha particles, beta particles, and gamma rays. And of course, we don't want any of that in our drinking water source. Now, 80% of exposure of radioactive material is from natural sources. 80% is from natural sources. Rock, soil, cosmic radiation from space, and radon gas. Only 20% from man-made sources. Now, EPA regulates the gross alpha emitters, beta particles, and photons. Now, radium-226 and 228 are combined, and as of 2000, uranium was added to the 4 radionuclides that we actually monitor. Now, radium can be a good thing. It's used in nuclear medicine for diagnostics, treatment, or research. It is also used to kill cancer cells for imaging, to produce steam, which turns to turbines to generate electric power, and smoke detectors. It's also used to kill pathogens and insects in your food. But too much of it will do what? Increase cancer risk again. Kidney problems. Regulation for all your radionuclides, 0. We don't want any of them present. That is the goal. The maximum contaminant level goal is 0. But there are, again, set limits for your growth alpha metals. You're looking at 15 picocuries per liters. Your beta particles, 4 millirems. Radium, 226 and 228, 5 picocuries per liter. Uranium, 30 micrograms per liter. So again, in 2000, that's when the addition of uranium was added to the radionuclides choice to monitor and report. We've already said that it gets in our water, 80% naturally occurring trace amount of body radioactive elements that are out there. So those are the ones of great concern to us as an industry. How do we treat, how do we remove these contaminants? If I were to ask you, how do we treat for bacteria, what would you tell me?
Disinfection.
Disinfection, very good. Can I disinfect to remove these inorganics? No. The only way that we remove these is a physical removal or physical process, or with the addition of chemicals and then physical, so it can be a combination. But disinfection does not remove inorganics. So, treatment options. Activated aluminum is one option. Again, it works well for arsenic, that was one, fluoride, as well as uranium, and selenium was one we did not talk about, but your activated aluminum can work well for it, or as aluminum-based material. Some of the operational issues when you're looking at the AA, though, it's highly pH dependent. So you want to make sure, again, you're operating in the right or optimum pH range for removal. That's going to be a major deal there. It says optimize at a pH of 6 to 6.5. 5 to 6 is optimal for anion removal there. So if it's outside of that pH range, you're not going to get the removal that you would desire. Another operational issue would be clogging. So, like with any other filter or something like that, you have to backwash in order to rectify that. And the media must be regenerated. It is low cost and minimum operator attempt to activate aluminum beds. Okay. However, on the flip side, you want to make sure that you have a game plan. What are you going to do with the backwash water brine, the rinse water, the acid neutralization water? Have a game plan for that. Can I just discharge it to the nearest waterways? Absolutely not. Not without a permit, meeting certain limits. There may be concentrated level of arsenic and radionuclides, which means now I got to make sure I have some type of waste disposal plan in place. So pre-treatment may be necessary if you're looking at disposing into a sanitary sewer. If you're planning on disposing of it to a sanitary sewer, you have to make sure you're following whatever industrial sewer use ordinance or sewer use ordinance that is in place in those regulations. Another option is the ions changed. This is a physical-chemical process in which ions are swapped between a solution phase and a solid resin phase. Chloride is released into the water. It is one of the best practices or technology for arsenic, nitrate, uranium, as well as fluoride. Here too we see some of the same operational issues as with the activated aluminum. It is pH dependent. So again, optimum pH for the resins, 6.5 to 9.0. It may be somewhat difficult to regenerate the resins with uranium exchange. So that will be something, if you have uranium as an issue, maybe something that you want to properly weigh. Total dissolved solids greater than 500 milligrams per liter will adversely affect the treatment performance. So what type of dissolved solids do you have coming in? What are dissolved solids?
Minerals?
Okay. Give me a little more. Give me an example of a dissolved solid. Ever had a nice glass of iced tea that you've added some sort of sugar or sugar substitute to it? What happens to the sugar?
Doesn't exactly melt down, but it's there.
In warm tea, what
Yeah, it's
happens
there.
to the sugar?
Dissolves.
Yeah, it dissolves. So if I filtered that tea, am I going to capture the sugar on top of a filter? Or does it pass through the filter with the tea?
Passes through.
It passes through. That is a dissolved solid. We know it's there. Yeah, we put it there. But it's dissolved in, and so it does not remain on the filter. Anything that remains on the filter would be a suspended solid. So that's a dissolved. So when you have them greater than 500, you're going to interfere with your treatment process. Pre-filtration is recommended if your source water turbidity is greater than 0.3 NTUs. So if your source water turbidity is greater than 0.3, then some type of pre-treatment may be needed. Intermediate operator skills is necessary for the anion exchange. We have the same waste disposal concern, your backwash water, your regenerant brine, your rinse water, your spent media. How are you going to handle that? Pre-treatment for spent brine may be needed for if you're going to dispose it to the sanitary sewer systems. And again, if they have a sewer use ordinance, you want to make sure that you are abiding by those parameters. Another option would be ion-based absorptive material. This is not considered one of the best technology or best available technology that's out there. However, it can be effective. This is one of the cases where they give you the variants where they say, okay, this is a cheaper way of doing it, although it's not the optimum or the best way of taking care of it. It can be effective for arsenic, radium, uranium, and antimony there. Again, pH dependent. Bacteria may accumulate in the media during low flow and hot weather. And if you're removing multiple contaminants, you can have a breakthrough of the contaminants that you've just filtered out. Waste disposal is a concern, so you may want to test to ensure the spent media is non-hazardous or radioactive. We have the mixed bed ion exchange. Here, anion and cation exchange resins combined in one single unit to remove the catatonic and the anionic contaminants. It is considered one of your best available technology or practices for arsenic, radium, uranium, sulfate, magnesium, as well as calcium. Optimum at a very high pH. Sulfate and uranium can displace arsenic from the resin, causing a spike of the arsenic in the treated water. Can be an issue. You can have contaminant breakthrough, which can be another issue. And you may need to increase alkalinity after the exchange in order to minimize corrosion in your distribution system. So again, when you're looking at these treatment options, look at your water, your source water, the contaminants you have in your water to see what will work best for your situation. Intermediate operator skill is required. Have the same issues with waste disposal, elevated concentration of radium and arsenic. Pre-treatment may be needed if you want to send it to the sanitary sewer. And then we have green sand filtration. Any of you all utilize this? You do at your surface plant?
Not the surface,
Or you do it at the
the ground.
groundwater plant? Okay. What do you think about it?
It's pretty much norm around this area.
Really? Okay. So here we got manganese coated filter media to oxidize and absorb the contaminant. It can be good for arsenic, radium, iron, as well as manganese up to a 10 part per million. How often have you changed your media out?
We basically pump the potassium permanganate back into it to restore it, so we refresh it that way.
Right. We do.
Typically, we don't replace the media for a long period
For a
of
long
time.
period, 20, 30 years,
Probably 15.
15 years. Okay. All right, operational issues, high iron to manganese ratio will lower the radiant absorption on the filter. pH greater than 6.8. Your radium removal improves as your pH increases over the range from 5 to 9. And you need basic operator skills. It's cost effective for radium removal at your small systems, especially those that can't afford the RO. This is an alternative. However, sludge supernatant from the filter backwash can be an issue. Elevated levels of radium and arsenic, if you have that, because now we have to think about disposal issues. Another option would be oxidation, coagulation, and filtration. We're adding a chemical to cause the clotting, and now that we have larger flog development, we're going to settle, then filter. So absorption of contaminants to an aluminum or ferric hydroxide precipitate removed by filtration. It is considered one of your best technology for arsenic, uranium, microbes, as well as iron and manganese. We have issues there also, pH dependent for arsenic and uranium removal. Advanced operator skill may be necessary also. You probably want to set up a series of jars in order for coagulant dosage. Iron, alum sludges, supernatant, filter backwash, spent media are all some concerns. Your backwash water can be discharged to the sewer or septic system, but you may have, if you have elevated uranium, it may dictate disposal option. And another treatment option is lime softening. Removes hardness by precipitating out calcium and magnesium, which are the two that will cause hardness. It is considered a best available technology for arsenic, for radium, for uranium, as well as hardness. It too is pH dependent. You see the thing that has been the thread throughout all these treatment processes. A lot of the processes we use will be pH dependent, regulating that pH. So it works well at a high pH. Advanced operator skill may be necessary. Here we have higher treatment costs. It is not a cost-effective alternative for small systems, and there may be a problem with alkalinity. If you have no naturally occurring alkalinity, you may have to increase alkalinity to control corrosion. So you don't want to choose an option that may create another problem for you. So weigh them well. Disposal concern, high volume of lime sludge, precipitates, radium or uraniums, supernatant from the sludge or filtered backwash. So again, you got to test what you're trying to dispose of to make sure it's not hazardous or radioactive. And then we have reverse osmosis. I call reverse osmosis a catch-all. What the other treatment options will not do, you'll probably get it with reverse osmosis. Reverse osmosis can handle all the radionuclides, all 4 of them. Reverse osmosis almost create a very purified water. Okay, so it is very beneficial. arsenic, fluoride, microbes, nitrate, radium, uranium, phosphorus, total organic carbon, most metals, sulfate, calcium, magnesium, potassium. What reverse osmosis is sending the water through under pressure a membrane. Okay, and it's going to remove quite a lot of small ions. Problems though, you can end up with easily fouled membranes. Your cellulose acetate membranes are susceptible to biological fouling, so you can use chloride with those. Your polyamide membranes can be damaged by chlorine, high iron, and chloramines, so that could be an issue. If you are using, as I said earlier, there are systems that use chlorination in conjunction with RO. If you're doing that, you want to make sure your chlorination is after your RO, because the whole purpose is to make sure you have a residual in your distribution system. So you would place it after the RO. Another thing that they're getting a lot better, because this number here used to be 50% or greater. Now 20 to 40% of your raw water is lost in the reject stream. That's a lot better than years ago, where you were losing over 50%. Advanced operator skill may be required, and it's a higher treatment cost. But in areas where all you have is salt water, may be the best way to go.
Higher operational pressure too, isn't
Yes,
it? A lot higher.
yes. So, treatment option tips, frequent monitoring, whatever option you're going to choose, treatment option, you gotta monitor. Okay, adjustment may be necessary to maximize treatment. Take into consideration the ease of operation. Take into consideration your operator's ability, capability to run the system that you have. Make sure, again, it's operator friendly. So operator qualification. Pre-oxidation may be necessary for maximum removal, so keep that in mind. And how do you have your systems set up? Are they set up in series or parallel? Which one will be more effective in order to get your desired result? And here they're looking at breaking the breakthrough of contaminants. With setting up in series, as it goes through this first one, you're going to be removing some contaminants. It goes to the next one, be a further reduction of contaminants. So you're probably less likely to have a breakthrough as opposed to sending all your water through parallel configuration. So test. Now also in your manual, subpart G is your drinking water regulation for your best technology. And that's on page 529 to 535. Subpart K is the variances for small systems. Again, this is only issued by the state exercising policy. Now, what was subpart H? We didn't say what subpart H was. Subpart H facilities are those surface water facilities or groundwater facilities under the influence of surface water. So surface water or groundwater under the influence of surface water. Are there any questions, comments, concerns, or issues on chemical contaminants? None? I am duly out of time. It's lunchtime, 12 o'clock, so we're going to pause here for lunch.